I'm Dr. K.V. Girija, Associate Professor, Department of Science and Humanities. I am going to present now the vector spaces, inner product spaces, and so on. Here, now our topic is vector spaces. In that, definition and properties we are going to see now. The definition of vector space, it consists of a set V and a field F, which are scalar, and two operations. First operation is vector addition, that takes two vectors u, v and w in V and produces a third vector written as v plus w belongs to V. Next is an operation called scalar multiplication, that takes a scalar C belongs to F and a vector V in V and produces a new vector CV belongs to V, which satisfy the following conditions. First condition is associativity of vector addition, which is U plus V plus W equal to U plus V plus W for all U, V, W belongs to V. Second property is existence of a zero vector. There is a vector in V written as 0 and called zero vector, which has the property that U plus 0 equal to U for all U belongs to V. Next, third property is existence of negatives. For every U belongs to V, there is a vector in V written as minus U and called negative of U, which has the property that U plus minus U equal to 0. Fourth property is associativity of multiplication, that is nothing but AB into U equal to A into BU for any A comma B belongs to F and U belongs to V. Fifth property is distributivity, that is A plus B into U equal to AU plus BU and A into U plus V equal to AU plus AV for all A comma B belongs to F and U comma V belongs to V. Sixth property is unitary T-mat property, which is 1 into U equal to U for all U belongs to V. These are the 6 properties to vector space. Next, inner product spaces. Let V be a real vector space. An inner product on V is a function denoted like this is V by V to R, which assigns each ordered pair U comma V belongs to V by V to a real number inner product of U comma V in such a way that the following axioms hold. First property is linearity, which is inner product of AU1 plus BU2, comma V equal to A into U1, comma V plus B into U2, comma V for all U1, U2 and V belongs to V and A, comma B belongs to R. Second property is symmetry, which is inner product of U, comma V equal to V inner product of V, comma U for all U, comma V belongs to V. Third property is positive definiteness, which is inner product of U, comma U greater than or equal to 0 for all U belongs to V and U, comma U belongs equal to 0 if and only if U equal to 0 vector of V. Now, inner product space. A vector space equipped with an inner product is called an inner product space. Example. Consider the vector space R power n. Prove that R power n is an inner product space with inner product defined by inner product of U, comma V, which is equal to A1 B1 plus A2 B2 plus etc. plus AN Bn, where U equal to A1 A2 etc. AN and V equal to B1 B2 etc. Bn. Solution. First, we have to prove it is an inner product space. We have to prove 3 properties. First one is linearity property. Given U equal to A1, A2, etc. AN and V equal to B1, B2, etc. Bn, W equal to, we are taking an extra C1, C2, etc. Cn in R power n, and alpha beta belongs to R, then alpha u plus beta v equal to alpha a1 plus beta b1, comma, alpha a2 plus beta b2, etc. plus alpha an plus beta bn. Now, alpha u plus beta v, comma, w is equal to alpha a1 plus beta b1 into c1 plus alpha a2 plus beta b2 into c2 plus etc. alpha an plus beta bn into cn. Now, what it represents? You collect all the alpha terms separately and beta terms separately. Alpha terms are alpha a1 into C1 plus alpha A2 C2 plus etc. alpha AN Cn plus beta B1 C1 plus beta B2 C2 plus etc. beta Bn Cn. Now collect all the alpha terms, alpha into A1 C1 plus A2 C2 plus etc. AN Cn plus beta into B1 C1 plus B2 C2 plus etc. Bn Cn. Now, alpha into alpha u plus beta v comma w is alpha into u comma w plus beta into v comma w. This is linearity property. We have to simplify like this. Next property is symmetric property. Symmetric property is nothing but inner product of u comma v equal to inner product v comma u. That is, we know that u equal to a1, a2, etc. an, and v is equal to b1, b2, etc. bn belongs to R power n. Now, inner product of u comma v equal to a1, b1 plus a2, b2 plus etc. an, bn, that is equal to b1, a1 plus b2, a2 plus etc. bn, an, which is nothing but v inner product of v comma u. So what you can write from this, inner product u comma v equal to inner product v comma u. This is symmetric property. Next is positive definiteness. In this, again, our u and v are given. Here we have to prove u comma u equal to inner product of u comma u equal to 0. Since and thus the given function is an inner product on R power n. Here we have proved that all the three property, linearity, symmetry and positive definiteness, hence R power n is an inner product space for the defined product. Next. In the same way, let us see the next problem, that this is the inner product with the standard inner product on R square. Here u is 1, 2. It is for R2, R power 2. In the previous problem, we did for R power n. And v is minus 1, 1, which belongs to R square. Then find w belongs to R square, satisfying inner product of u comma w equal to minus 1 and v comma w equal to 3. Now we are going to find out what is our w value. Now let us take w equal to a comma b belongs to R square. Now what is given? Our inner product of u comma w is minus 1 given and v comma w is 3 given. What is that? Our a, b, how can we write minus 1? To find out the inner product values, we will multiply a with 1 and b with 2. So it is a plus 2b equal to minus 1, it is given. And similarly, ab with minus 1 and 1, we will get a minus a plus b equal to 3. When you are solving this, a plus 2b equal to minus 1 and minus a plus b with equal to 3, we will get a ordinary solving, we will get a equal to minus 7 by 3 and b equal to 2 by 3. So our w is nothing but minus 7 by 3 and 2 by 3. Now, next problem is angle between vectors. The angle let V be the inner product space. U and V are the two non-zero vectors in V. The angle between U and V is defined to be the angle theta such that 0 less than or equal to theta less than or equal to pi and cos theta equal to inner product U comma V divided by norm U into norm V. This Now let us find out a problem. Let us do a problem to find out the angle between two vectors. Here R cube is the inner product space with respect to standard inner product. Find the angle between the vectors u equal to 1, 1, 2 and v equal to minus 2, 1, 1. Let theta be the angle between u and v. Now we know the formula cos theta equal to u comma v by inner product u comma v divided by norm u norm v. Now we know how to find out inner product. Inner product value is 3. That is, we are multiplying 1 into minus 2 plus 1 into 1 plus 2 into 1. So the value is 1. And norm u equal to root of 1 square plus 1 square plus 2 square. It will be root 6 and norm v equal to root of 1 square minus 2 square plus 1 square plus 1 square will give root 6. Now cos theta is nothing but 3 divided by root 6 into root 6 which is 3 by 6 which is half, and cos theta equal to half. Theta is cos inverse of half which is nothing but 60 degree which is pi by 3. This is the way to find out angle between two vectors. Now in this slide in this topic we have seen how to find out check whether the given vector space is an inner product vector space, and we found out the angle between two vectors. Thank you.